Today's notes are on one of the most challenging topics in all of mathematics, something called induction. Now, I remember when I took calculus back in college, about half the people in my calculus class had seen induction before, and about half the people hadn't. Those who had seen it had a huge advantage, even if they didn't fully understand it at that point. They just had a head start on those people who had never even seen it. So we're going to introduce mathematical induction. If you kind of get it, you're doing all right, and hopefully you can go even farther than that. Hopefully we can get it. So two main kind of problems today. First one isn't really induction, but just a different kind of problem here. So first example, we want to find a formula for the nth term in the sequence. So we've been talking sequences and series. Now, here's the deal with this particular sequence. If we add a common term here, well, it's just not going to work. We're adding 2, then 3, then 4, so I guess we never really add a common term. So let's see if we can multiply by a common term to get the next term in the sequence. And if we try that, well, 3 times, actually we go times 5/3, 5 times 8/5, 8 times 12/8. So again, we're not multiplying by a common term. So this is not an arithmetic sequence. It is not a geometric sequence. Different kind of sequence here. Now, you might have noticed that when I did see if it was arithmetic, that we did see a pattern here. We're just adding the next progressive integer. And notice the difference between those additions is 1 every time. So we're looking for a common difference, and we don't get it right away with our first step. But if we take another step, we do get a common difference. So on this kind of problem here, it takes us 2 steps to get a common difference. Here's what that means. This is not arithmetic, this is not geometric, but it means that we can come up with a sequence, and since it took 2 steps, this sequence is going to involve something to the second power. So here's what our sequence is going to look like. It's going to be a sub n, the nth term equals, and then we need a general equation of some polynomial function to the second power. So it's going to be something, I'll just call it a, times n squared, plus something, I'll call it b, times n, plus something. Okay, so in general, here's this equation. It's y equals ax squared plus bx plus c. Now we've seen these kind of problems before, and in fact we've seen some problems like this where we had to come up with this kind of equation if we were given 3 points that a parabola goes through. So I'm just going to write some more information up top. N is a term number, so first term, a sub n, the value was 3. Second term, the value is 5. Third term was 8, etc., etc. Now, n kind of works like our x. For every x value, we get a sub n kind of works like y. So here's what I want to do. Let's take the first 3 points. And why do we need 3 points? Well, remember, anything to the second power, we need a general equation using 3 points, or actually 3 general equations. So I'm going to plug 1 in place of x, or an n, depending on which one of these you look at. And I'm going to plug the 3, 5, and 8 in place of y. So let's put the y last. So let's put 1 in place of x here. So 1 squared is 1 times a, plus 1 times b, plus c equals the y value, which is 3. Let's plug 2 in place of x here. If we plug 2 in there, we get 2 squared, which is 4, times a, plus 2b, plus c equals 5. And let's plug 3 in there. If we plug 3 in there, we get 9a, plus 3b, plus c equals the third term, which is 8. So we're plugging 1, we're plugging 2, we're plugging 3 in place of x, and we're plugging 3, 5, and 8 in place of y. Now once we have this system of equations, we need to solve for a, b, and c. We saw a huge shortcut last week, where we have to put these coefficients, put these terms in a matrix, and then use reduced row echelon form. And go ahead and we can plug that in and use our calculator for that. So remember, we want to put that in as a matrix, use our reduced row echelon form. If we do that, here's what we find. We find that A equals 0.5, or 1/2. B also equals 1/2, or 0.5. And C equals 2. Now careful, that's not your answer. Your answer is going to be this equation here with these coefficients plugged in. So to find the nth term, a sub n equals, we can put these coefficients in. We take 0.5 times n squared plus 0.5 times n plus 2. And we can test this here. I'm just going to pick some random value. Let's pick this one. If we plug 4 in place of n, 4 squared is 16, 10.5 is 8. Plugging 4 in again, 0.5 times 4 is 2. Then another 2, this adds up to 12, which is what we expect. So now to find any term in this sequence, we can plug the term number in place of n, and the value we will get will be the value of that next term in the sequence. Okay, so this process here, this method, can be used if we don't necessarily have an arithmetic sequence or a geometric sequence. We look at the number of steps it takes to come up with that common sequence. So let's look at one more like this. Okay, and I'm looking for a common difference here between these terms. Notice first set of terms goes up by 3, then 6, then 10, then 15. So not a common difference. Let's look at the next steps. It goes up by 3, then 4, then 5. So once again, not a common difference. But now we can go up by 1 every time. This took 3 steps to do. So that means my final equation is going to have something to the third power. So it's going to look like this. A sub n equals something times n to the third plus something times n squared plus something times n plus something. And in fact, I'm going to just put this a sub n at the end so we can plug everything in, use reduced row echelon form. So n is my term number, a sub n is the value. And if you prefer using x and y, that is perfectly okay. Now since we have something to the third, we're now going to need 4 equations. So if we plug 1 in place of n, we get 1a plus 1b plus 1c plus d equals a sub n, which is 2. Next term, plugging 2 in there, 2 cubed is 8, so we get 8a plus 2 squared 4b plus 2c plus d equals a sub n, which is 5. Let's plug 3 in there. 3 cubed is 27. So we get 27a plus 3 squared is 9b plus 3c plus d equals 11. And last one, if we plug 4 in there, we get 64a plus 16b plus 4c plus d equals the fourth term, which is 21. Now one thing you'll notice these coefficients are all the fourth powers. Here's our, third powers. Here's perfect squares. Here's the numbers 1 through 4, just 1d. You'll see that every single time. And again, we know if we use reduced row echelon form on these coefficients and answers, we will get a solution of, I'm just going to jump to the solution here. A sub n equals 1/6 n to the third plus 1/2 n squared plus 1/3 n plus 1. And there's our general form for any term in this sequence. Okay, so that's our first kind of problem today, and that's challenging enough, but we're going to put another challenging problem in here as well. We're going to talk about something called induction. Now, we've been talking about how to come up with a general formula. Induction is a proof. It's a way to prove or to show that a general formula works. And here's the analogy I use when I teach induction. I say, think about knocking down a set of dominoes. In order to do that, the first thing you have to do is knock down the first domino, obviously. And then every domino is going to hit the next domino. And it's going to go on and on forever, for however many dominoes you have. So our two steps of induction are very similar. First, show that our formula works for the first term, which basically means plug 1 in place of n. And then show that no matter what term you pick, and k just stands for any general term, the formula will also work for the next term, the k plus 1 term. Okay, let's jump right in. So next example. Here's what this is saying. If we add up a series of odd numbers together, let's say we add 4 odd numbers, it'll add up to 4 squared. If we add 100 odd numbers, it'll add up to 100 squared. So this just shows these odd numbers. This shows what in that case, what the 100th odd number will look like. 2 times 100 minus 1, it'll be 199. So this is saying if we add up a progression of these numbers up to this last one here, the answer will be n squared. Now this is something that is true, but how do we know it's true? Well, that's where induction comes in. We want to prove that this is true. So first step, we want to show that this works for n equals 1. Well, when n equals 1, we're just talking about the first term. N is the term number. So we want to see, does this work for the first term, which is 1? Does that equal what we get when we plug 1 in place of n? Well, 1 squared is 1, so yes, indeed, it works. And the first step, I often say, is the easy step. So really it just means plug 1 in place of our n, and see if that number equals what the first term is over here. Okay, now the tough step. Second step, and this is going to take a little bit of work here. We want to assume that this sequence works for any value k. So we want to assume that this is true. 1 plus 3 plus 5 plus 7 plus ... plus, I'm going to put k in place of n. K just stands for any number, and that's going to equal k squared. We want to assume that this is true. So now what we want to do is we want to show that it will work for the next term. So basically I write down exactly what I had before. Plus ... plus 2k minus 1. But then I want one more term. So plus. Well, how do I get one more term? Well, to get one more term, I'm going to plug k plus 1 in place of n up here. So it's going to be 2 times k plus 1 minus 1. We want to show that that equals what we get if we plug k plus 1 right here. So k plus 1 quantity squared. Now how on earth are we going to show what's on the left is equal to what's on the right? Alright, here's the key step coming up right here. All of this stuff right here is the same as all of this stuff above. Now if we assume what's up here above is equal to k squared, we can make a substitution right here and say all this stuff down below is still equal to k squared plus. Now let's bring everything else down. But while we do, we might as well simplify some things. So I'm going to write this as 2k plus 2 minus 1. So that's all of this equals, now this k plus 1 squared, I'm just going to write it out twice and multiply it together. That'll give us k squared plus 2k plus 1. Now, is what's on the left equal to what's on the right? Sure it is. Let's combine our like terms. On the left, we get k squared plus 2k plus 1, which is the same as what we had on the right. So basically, we have shown, since what's on the left equals what's on the right, that means that this does work for any term in the sequence. So let's talk about why this works here. So if the first term works, we're good. Then we're saying any term along the ways, if we assume it works, the next term will work. So if the first term works, the second will work. Then the third will work. Then the fourth will work, etc., etc. We can keep going on and on forever. Basically, any term we pick, if this works, the next term will work as well. So we have just proven that this equation is always true using induction. Okay, I warned you, it's a tough process. Let's try one more of these. We want to prove now that if we add any series of integers together, the answer will be equal to this. So if we add 100 numbers together, we'll get 100 times 101 divided by 2. Okay. let's prove this. First of all, we want to prove that it works when n equals 1. So we take the first term here. Does that equal what we get when we plug 1 in over here? So 1 times 1 plus 1 all over 2. Yeah, 1 equals, so that is going to be equal, so check, yes, it is true. Okay. Second step, now we've got some work to do. We want to assume that this on the left will work, or actually this entire equation will work for any value of k. So I want to assume that if we plug k in place of n, and really k just stands for any number, so we want to assume that anything we plug in place of n will make this true. So in a sense, this first part of this step is just taking what we have up here and plugging k in for all of these n's. So if that's true, we want to show that if we go one more term, it'll still work. So if we go one more term, I can bring down everything I wrote above and then add one more term. Well, how do we know what to add? Well, we take this last term and we plug k plus 1 in this spot. We're just going to get k plus 1 there. Now over here, same thing. In all these spots, we want to plug k plus 1, so that'll give me k plus 1 times, in parentheses, k plus 1 all over 2. Okay, here's the key step. All this stuff down here, 1 plus until you get to k, is the same as all this stuff up above. Up above it was equal to this. So let's do a substitution. So k times k plus 1 all over 2. Now everything else we can bring down. So I'm going to say plus k plus 1. Does that equal what we get over here? And I'll simplify a little bit while I bring it down. So k plus 1 times k plus 2 all over 2. Okay, now it's going to take some algebra. This one, the algebra is going to be a little tougher than the last one, so I'm going to distribute first. So we get k squared plus k all over 2. And here it would be nice to have a common denominator. So I'm going to multiply top and bottom here by 2, which if I distribute that throughout, I get plus 2k plus 2 all over 2. Does that equal, now let's multiply this together using the distributive property. K squared plus k plus another 2k plus 2 all over 2. Now since we have common denominators, we can combine these like terms. So on this left side we get k squared plus 3k plus 2 all over 2. And if we combine like terms over here, guess what? It's the same thing. So we have just proven that for any value of k, if we assume that it works, the next value will always work as well. So we've just proven this original equation always works for any value of n using induction. Okay, I warned you, induction is a little bit tricky. You definitely need to practice this. There will be one of these on your next test, so get some practice on this. There's a few homework problems to take a look at. The first few are like the first few problems in our notes. The last two are like, actually I think the first few are induction. The last two are like the first couple problems in our notes. So check that out. Definitely get practice. These are very, very difficult problems. Do not just try to do these with no practice. So get some practice on this. It does get easier, I promise.